Hi everyone, and welcome to this video on deriving the steady state output, investment, and consumption in a simple Solow growth model. So before we begin, let's first define or recall what a steady state is. So a steady state equilibrium is essentially an equilibrium that occurs when all variables under consideration for our model, which in this case is a simple three equation model, are growing at a constant rate, which basically means that today's growth or today's value, in effect, is equal to tomorrow's value. So just to recall, right? So if you recall, in a steady state, if we have, say, a variable like capital, so capital tomorrow is the same essentially as capital today, right? So it's not growing. And we can, because they're the same, so in the steady state, we'll just make it K star, right? So basically, the capital today, the capital tomorrow is just the same because they're not growing. All variables are growing at a constant rate. So we have some constant value. And essentially what we're going to do in this video is we're going to solve for steady state capital, and we will get output in return, as well as investment, as well as consumption, right? That's what's gonna happen. And we're gonna try and see how those many things are interpreted. So we can begin. So we have here, you can see here in the slide that we have three equations in our model. The first equation is the production function. And the way that we sort of describe that is our production, which is YT, this is output, is some function of AT, which is some technology shock. This is a technology shock. And you also have here KT, which is capital, raised to alpha. And this alpha term here is like a returns to capital, something like returns to capital. Then our equation, the next equation that we have is our aggregate resource constraint, which we have here consumption. And we also have here investment. So notice in this simple model, we don't have government expenditure, we don't have exports, we don't have imports, nothing, just a simple model. And our last equation is our law of motion of capital. So you have tomorrow's capital, and which you determine today, right? KT, which is today's capital, some fixed value. And you have delta here, which is the depreciation rate. Depreciation rate, right? So we have those things there. So let's sort of first, okay, so the first thing we're gonna do, so first, okay, let's try, okay, to form sort of the three equations into just one equation, to collapse into one equation. So what we have here is, so you can see we have numerous YTs. So I'm going to take this aggregate resource constraint. So that's YT is equal to CT plus IT, right? That's YT is equal to CT plus IT. But I know that YT is equal to AT KT alpha. And I know that CT is just CT. And IT is equal to the law of motion of capital equation. So that's KT plus 1 minus 1 minus delta KT, right? So we're going to work with this equation. Let's call this star, right? Then we're going to do, okay, after this, we're going to appeal to our steady state condition. So if you recall, in the steady state, right, all of these things are growing at the same rate. So effectively, we can replace all variables with T subscripts to just have a superscript, star, right? Like what we had here, right? So because the variables aren't growing, regardless if it's today or tomorrow, it's the same value for a particular variable, right? So basically, this star equation transforms into this new equation. So you have except A. So let me just reformulate A. I sort of mistyped here. This is just a normal A. This is not AT. We're not in the neoclassical model yet. So that's just a regular A. So we have here, or actually we could have an AT, that's fine. It wouldn't really matter, like thinking about it now. So we have A star, K star raised alpha, right? Raised to alpha equal to C star plus K star minus 1 minus delta K star. So notice this was KT plus 1. This is KT. At a steady state, they're the same thing, right? So there's no distinction between them across periods because we're at the steady state. Now, just recall, okay, so from the basic intuition of the Solow model, we know that savings, right? Savings is a constant, okay? It's a constant proportion. It's a constant function of output, right? So the way we define savings, right? Because in the Solow model, savings is equal to investments, right? So we know that S is some proportion, right? So savings, ST, is some proportion little s times YT or output, right? And we know that this is equal to investment, right? And just to make it clear, S, little s is some proportion between 0 and 1, right? Between 0 and 1. Then, okay, then we know, okay, basically that whatever is not, so if you look at your aggregate resource constraints, so just zeroing in here, whatever isn't invested or saved is consumed, right? So we can effectively, rewrite consumption. Consumption is equal to 1 minus S, which is the proportion of Y which you don't save, right? And that's basically consumption, right? And basically, if we substitute, okay, if we substitute that, okay, for C T, expressing, everything effectively now in terms of capital, pressing in terms of capital. So just to get you to know what I mean here, CT is equal to 1 minus S times YT. But YT, right, is 1 minus S. I'm sorry, the YT is going to be, that's going to be AT times KT alpha. But at the steady state, right, at the steady state, okay, we have C star is equal to 1 minus S A star K star alpha, right? So that's that. So, okay, what we have now is we have, let's try and merge things together using, again, the aggregate resource constraint. So just bear with me here. We have A star K star raised to alpha. This is your YT, I'm sorry, not YT. This is steady state. This is Y star equal to, right? The next thing in the aggregate resource constraint, that's CT. So we need C star here based on this one. C star, is this one. That's 1 minus S times A star K star alpha. So this thing here is C star plus investment. Now, investment here is basically this one. This entire thing is the law of motion of capital in its steady state. So that's K star minus 1 minus delta K star, right? And this is your steady state investment, right? I'm sorry, well, that representation at this particular equation. Now, if you notice, the equation is still in terms of endogenous variables, right? And as much as possible, we want to express, we're deriving these steady state values. We want these steady state solutions to be in terms of the exogenous parameters that we have. So we want them to be some function of our alpha, our A, our delta, and S, right? So we want these things to be just functions of the endogenous parameters, right? So uh, let's try to observe these things again. Notice that the only endogenous variables you have is KSS, right? That's still endogenous in this particular equation. That's just KSS. So if we're solving for steady state capital, we have the solution for KSS in terms of, we could have a solution for this KSS in terms of the other parameters. And these other parameters are your A, your alpha, your delta, and your S, right? So it's simple and straightforward to solve for that. We just need to manipulate this equation. So manipulating this equation, right? So this is again A star, K star alpha equal to, so if we sort of get this one, so this is 1 minus S, A star, K star alpha plus K star, then let me distribute the K star to the 1 minus delta. So you get minus K star plus delta K star. And obviously this one will drop off, right? Then we can simplify now further, right? So what you can see is if we distribute this one to both here, so we get A star K star alpha equal to A star K star alpha minus SA star K star alpha plus delta K star, right? And obviously, if I transpose this to the other side, those things would cancel out, right? Because that would be negative and this is still a positive. Then I'm left here with minus SA star K star alpha plus delta K star. So what I do now is I transpose this one to the other side. So I get positive SA star K star alpha equal to delta K star, right? So I have that delta K star. And what I want to do, okay, just so that I can make it a function of, so let me divide both sides by K star. So that takes out the K star here. So I'm left with SA star K star alpha over K star equal to delta. Then let me, again, divide both sides by the other parameters that are there. So that's S times A star, right? So let me multiply that one by that. So I'm going to be left with, so that one will cancel out there. So I'm going to be left with K star alpha over K star is equal to delta over SA star. So here we can simplify this easily, right? So the exponent of the numerator is alpha. The exponent of the denominator is 1. So this is basically K star raised to alpha minus 1, right? Raised to alpha minus 1. That's equal to delta over SA star. But, you know that alpha lies somewhere between 0 and 1. So this is sort of not a good solution to it. So what we can do is we can sort of reverse it by raising both sides or to -1. So we can get a K star raised to 1 minus alpha, which would now be positive because alpha lies between 0 and 1. But in doing so, we need to flip the other side of the equation. So SA star will now be in the numerator. Then delta will now be in the denominator. Then to get steady state capital, as a function of the other exogenous parameters in the model, then what we can do is to just raise both sides to 1 over 1 minus alpha. So I now get steady state capital, which is K star is equal to S A star all over delta times 1 over 1 minus alpha. And this is your steady state capital, right? So that's steady state capital. And that solves that. Now, let's sort of explore what this means, right? So notice in our numerator, we have the savings rate. So this is the savings rate. Then we have technology shocks, right? Technology shocks. And then in the denominator, you have depreciation. So obviously, right, if S increases, if the savings rate increases, and if there's a positive technology shock, that's good. That increases steady state capital, that increases capital. But if the depreciation rate goes up, the one in the denominator, it decreases steady state capital. And pretty much that's what we expected, right? That's what we expected. So we have our steady state capital here. Now we can just solve quite easily for steady state output. So let's now solve. So we're going to solve for steady state output, and the steady state output is quite simple. So if you recall, okay, our equation yt is equal to at times kt alpha. But at the steady state, so at the steady state, we get y star, which is steady state capital, is equal to a star times k star raised to alpha. But again, we already have K star. We solve for it. That's this one, SA star over delta raised to 1 over 1 minus alpha. So we can get Y star by just plugging that in. So Y star is equal to A star times, okay, we have here S A star all over delta raised to 1 over 1 minus alpha, but we need to raise this one to alpha, right? Because there's an alpha term here. So basically, our steady state output is quite simple. That's just A star times, okay, SA star all over delta times alpha over 1 minus alpha. This is our steady state output. Okay, quite easy to solve for. Now, since we have steady state output and we solve for steady state capital, we can easily solve, okay, the other things there. We could get steady state investment, and of course, we can get steady state consumption, right? So let's solve for steady state investment first. So solving for steady state, okay, steady state investment, right? So solving for steady state investment, we know that I star is just equal to ST, right? Or the savings star. So no more S, no more T. And this is just some proportion S times Y, right? And in this case, at the steady state. But we know Y already. So ISS is pretty much the steady state investment is just I star, which is equal to S times Y star. So S A star times S A star over delta times alpha over 1 minus alpha. And that's pretty much steady state investment, right? Last, we can get, so solving for steady state consumption, we get C. So if you recall, again, C star is basically the proportion, which is 1 minus S times Y star, right? Here at the steady state, of course, because whatever we don't invest or save, we consume, right? So that's the proportion 1 minus S. And that's basically as simple as steady state investment. C star is equal to 1 minus S, 1 minus S times Y star, which is A star times S A star all over delta times alpha over 1 minus alpha. And that's C star there. So we have solved for all the steady states here, right? Now, just as a final activity, let's just try to graph this very quickly. So, so let me graph the Solow model, sort of like as a segue to the next video, graph the Solow model. So we have the three equations that we have. So let's try to get some identities from there. So we have here YT, right? YT. And we have here KT, right? So our first is the production function, and it's just, again, strictly increasing, an increasing, but a concave graph here. So that's YT is equal to AT, sorry, capital AT, right? AT, KT alpha. And then we have IT, our law of motion, our investment, which is, again, some proportion of this output, right? So it's somewhere here, I guess, here. So we have here IT is equal to KT plus 1 plus 1 minus delta. Sorry. It's minus 1 minus delta KT. And we have here our depreciated capital line somewhere here. Call it here. That's delta KT. So basically, what we'll sort of explain as we move from now is this intersection here, right, represents our steady state capital, right? Will basically fall under, that's K star, right? That's steady state capital. And if we bring it up to the production function, this one will be our steady state output, Y star, right? And this one, matching with or intersecting with the investment line, with the investment curve rather, this is I star or steady state investment. And as you would see, again, the difference between Y and I is just C. So this entire thing in the middle, this is just steady state consumption, right? So that's basically the Solow models and how we derive the steady states in the Solow model. So thank you for your attention, and I'll see you in the next video. Thank you very much.